have burning questions that they want to interrupt me with, feel free. Those back and forth conversations are normally quite nice when we do presentations like these. So yeah, I'm Damien. I'm from the University of the West of England. I'm within a research centre called the Centre for Fine Print Research. Yesterday was actually my last day there. So as of Monday, I'm actually at the University of Nottingham, moving into Nottingham at a bit of a funny time, but it's exciting anyway. So if anyone happens to know any good walks or anything around there, do let me know. Or if you happen to know a good pub, that would be good too. So I'd start off by just kind of giving you an overview of the talk. Most importantly, if I do run over time, let me know, and I'm quite happy to wrap it up quite quickly at any point. So I'll start by telling you who I am, what I know, and more importantly, all the things I don't know. Then we'll talk a little bit about pigment, color from pigment, why paints look the way they do. And then we'll move on to structural color. This is really why nature is a kind of a fantastic engineer, a fantastic designer, because they do something really different from what we would do in terms of coloring things. And it's really quite a fascinating topic once you start to crack into it. I'll be focusing, I'm afraid, quite a lot on things like beetles and butterflies, because those are really simple examples of this effect. And it turns out the seashells are incredibly complicated, but don't worry, we'll get there. And hopefully we'll have plenty of fascinating discussion about it. So just quickly, who I am. I'm actually a physicist. I did my PhD over in Bath Uni. I took a little bit of a left turn after PhD and moved into print research. So these days I work on additive manufacture and looking at bringing back 19th century print and photography techniques and modernizing them and all these things. And also material science. So just a couple of things that I've done. This is a Woodbury type, which is a really obscure printing technique based on gelatin. These are some liquid crystal films that we've made. This is my cake printing machine. It doesn't print the cake, it prints the icing on the cake, but that's quite nice. So at the heart of it, I'm not really a biologist. This is something I do because I find it really fascinating, but that does mean there are some big holes in my knowledge. So if I am saying something incredibly wrong, do let me know, because I'm really interested in this topic and I'd love to be right about it. But essentially where I'm from in terms of physics and engineering and things like that, biological structures and biological materials are currently a really interesting topic. A lot of what's going on these days are people are looking at the kind of tricks and skills that nature has put forward and evolved, and using those as inspiration for their own designs. So it's, like I say, it's all about learning the tricks and attempting to recreate them ourselves and utilize them in engineering topics and physics topics that we could start to apply to everyday life. So material appearance, it's a funny thing. We'll start by playing a quick game. In terms of responding to this, you can write in the chat if you want. I might be able to see it, I'm not quite sure, but it doesn't look like it. Either way, find an object around you, any old object, and if you can't find anything in particular, just use a wall nearby, and attempt to kind of describe to yourself the material appearance. What does this look like is the question you want to ask. And the rules are, you can't use the name of the object, and you can't describe the silhouette. So you're not worried about the object itself, you're more worried about the materials that make up the object. So if we were to look at this pipe here, this pipe that is not a pipe, you could start to say, okay, well, there's some wood to it. There's this glossy kind of sheen running along the side here. It's obviously been polished in some way. There's a metallic finish. This is colored differently. Maybe it's a paint, maybe it's a different type of wood. Couldn't be sure. But these are the types of questions that I have to ask myself a lot in research. And it really is, once you start to ask, what does something look like? It becomes quite a complex question. So materials can really be boiled down to 4 visual qualities. You can start to think about color. So these powdered pigments in the top right here, they're all quite obviously a powder, but you can tell the difference between them just based on the colors. There's texture. So this rough wall surface down here as opposed to the smooth surface of the laminate flooring, you can start to make some assumptions about the materials just based on the differences between these two. There's gloss, which is basically a measure of the kind of reflectiveness, the shininess. So this glossy paper, you can see very obviously it's shiny. And again, your brain can start to think about the way that that would feel just based on the way it looks. And finally, the fourth one is a little bit of a strange one, but it's translucency. So we can see some of the city of San Francisco over the top here, but the bridge is somewhat partially obscured by the clouds. But that doesn't mean it's not there. We can still see it partially, just because these clouds are slightly translucent. And this is an image of a bygone time when we could go to the pub and stand this close together. But the sunlight is coming through the beer because the beer is slightly translucent. Again, this is part of its material appearance and part of the way we would use to describe what does it look like. All of these things can vary to make it even more complex. Things like the lighting, the viewing angle, our distance from them, and even the observer. So inherently within our own eyes, we have some biases towards certain colors and wavelengths and things like that. So that affects the way we see things as well. But if you want to make the question even more complicated, what you say is, why does it look like that? So these sorts of things have kind of plagued physicists for centuries, really. Isaac Newton he did some incredible stuff with light and matter. What he was really interested in was the way that they interact together. So there's this famous experiment where he blacked out his room and he put a little hole in one of the curtains and placed a prism up to the beam of light that was coming through it, and noticed that it all diffracted out into their separate component colors. Finding out that white light was made of other colors was really a kind of a fun turning point. And this idea comes up a lot in science. So when you're working with light and when you're working with materials, we can use one generally to infer the other. So if we have a material and we don't know what it is, quite often we will probe it with light in order to look at the way it responds, and vice versa. If we have a type of light and we don't quite know what it is, we can use forms of matter to look at how they interact with it and how they respond to it. All of these things really mean that the answer to the question, why does it look like that? Well, there's a lot. The two main ones that I want to focus on are kind of the size of the components and the structure. By that I mean, if you look at all this copper here, this is all types of copper. One is the kind of the copper we know, the metallic copper. But if we change the chemistry a little bit, we can get this blue powder. So it's these fine little crystals all put together. And if we change the chemistry a bit more, we can get this red powdery material. Add a little bit more oxygen, the color changes again. These are all, again, parts of why does it look like that. It's the chemical composition, the lighting, the viewing angle, the distance, the observer. All of these things and more can really change why things look the way they do. So again, going a little bit deeper into kind of color and all of these things. This will all come back to, I promise this is going somewhere. Color really is only one small part of a much bigger spectrum. So this spectrum involves things like radio, microwaves, X-rays, and we only see this very section. It's quite strange to think about that, because that means we're seeing only a tiny little bit of what's actually going on around us. We can't see microwaves, we can't see radio waves, but they're still waves. They're effectively the same thing. Then of this tiny little window that we see, again, we have some interpretation due to our eyes. So our eyes have three types of cones in them. They're called small, medium, and large, effectively. The small cones are biased towards blue wavelengths, so they see blue colors better. The medium ones are biased towards green, and the longer ones are biased towards these kind of yellow, oranges, and reds. So this is the way we see color. This little plot over here is a fun thing called the psi XY chromaticity diagram. It's good fun if you're into color, because everything that exists within that little arc there is all the color that we can see. There is the added addendum that, you know, we can see all of these colors darker and lighter as well, but really it's quite strange to think that this is all the color we can see. And also as a quick side, like a fun side note, you might notice that the green portion of the graph is absolutely huge. So our eyes are tuned really quite tightly towards green wavelengths, which is quite interesting when you consider, you know, our place within nature. We see a lot of green things, and we can distinguish between a lot of green things quite well. So let's go back to paint. As I mentioned, white light is effectively a combination of all colors. So if we have our red paint on a surface, the white light comes in. What happens is the red paint absorbs the blue and the green components of it, and it chucks out the red. So that's kind of unintuitive, it's kind of counterintuitive, in that the color we see objects as traditionally is the color that's rejected by the pigments. So it's the one that it doesn't need. So everything that's left behind is what we see. And the fun thing about that is that if I look at this, this is a scanning electron microscope image, and we zoom in, effectively what we see here is the wall underneath, and this is a film of paint. The thickness here is around 100 microns, which means it's about as thick as a human hair. And if we look at it, you can start to see little baubles kind of sticking out the side here where I've cut it in half. These are just little bits of pigment, and they're kind of scattered randomly throughout. The strange thing here is that if you move about all the pigment atoms and you kind of change their places, once we zoom out again and look at the red wall, it would still have the same color, because these pigments are dense enough and strong enough that they just would make it look red. But taking a more biological system, in this case the leaf, we'd say, you know, why is the leaf green? It's mostly chlorophyll. So our white light comes in, it hits the leaf, the chlorophyll absorbs the blue and the red, leaving behind the green, which it has no purpose for, and chucks it back out, leaving us to see these nice green leaves here. So, looking around for another example of this in nature, you'll notice that there are maybe different types of colors. This is an image of two beetles, for instance, that I've chosen because they're at slightly different angles from one another. Basically, you could see these two pictures, and you could quite easily say that there is something slightly different about the types of green here. Maybe it's the color, maybe it's the appearance, maybe it's something to do with the material. As I mentioned before, all those reasons for why things can be the same but look different. But this has something else going on, something else a bit more complicated. So if we zoom in a little bit on the beetle, you'll find very immediately that it's green, but it's not just green. So what I've done here is I've just taken this little image and I've chucked it into Photoshop and just used the little eyedropper tool to actually check out what the colors are at each point. So what happens here is if you take this top portion, you'll notice it's a nice dark green, as we expected. As you move a little bit further down, it turns into a yellow. And if you move down a little bit further, it turns into an orange. So we've seen this ordering of colors before when I showed you the white light spectrum, and that's because they're all right next to each other in terms of wavelengths. That means they're all quite similar. You just change the wavelength a little bit and the color changes. So there's something going on here that means that all these things are related. And this is actually something called iridescence. In terms of shells, you might have heard the term pearlescence or luster. These are all kind of the same thing. I tend to use iridescence, so just for future notice, they're kind of interchangeable, but hopefully that makes a little bit more sense. So in terms of Beetlejuice, you've probably heard a little bit about insects and things like that being a component in classic pigments and paints and food colorings and all these things. There's the classic story about how blue Smarties were made with crushed insects. And these are true. This is something that happens. For instance, carmine is a very famous, really strong pigment made from this cochineal beetle. And effectively, the old school way of obtaining that pigment was to just collect as many as you can, crush them up and process them a little bit. So does that mean that we could do that with any old beetle? The green beetle that I showed you before, could we take those, take the shell off, crush it up and just apply that to a wall to get some nice green paint? The answer is actually kind of no. It's strange, but it really means that within the beetle there is very little pigment. There is no green pigment. In fact, there is only black pigment, which is a strange thing to think about. So what's the difference? This is that structural color that I mentioned. It's a different sort of color. Whereas before things were using pigment, this is using structure. This arises directly from the interactions of light with the nano and micro scale. So it is looking at really tiny architectures that are embedded within the animal that interact with the light directly and have no need for pigment. Often this gives it a kind of metallic appearance. These colors will shimmer and they will change. And again, this leads back to probably all the kind of properties that you would associate with the word pearlescence. And they vary, again, depending on the viewing angle and the lighting. So these are some more obscure kind of examples of this, particularly within beetles. So in terms of the physics, this is because the outside structure of a beetle is actually very, very complicated. It's not just one structure. What it is actually these alternating layers. So I've kind of shown them here by the lighter sections and the darker sections. These are alternating layers of a material called chitin. Sometimes these other layers can be chitin with a little bit of water in, or a different kind of proteinous membrane. But what happens is white light will enter this, this material, and at the very bottom there's a pigmented melanin surface. That means that any excess white light that comes in is absorbed. But we see a color. So what is that color? In this case, I've said it's these green portions coming off. There's no pigment in these layers, so it's doing something different. And actually what's happening is the colors reflected are chosen by the properties of the material, so the type of chitin and the interaction going on there, and actually the thickness. So the thickness matters a lot. Typically you'll find that many species have very similar structures, but all they do is they vary these separations and they end up with different colors. So I'll show you some examples of that in a minute. This might sound a little bit strange, and it is a little bit strange, you know, color without pigment and all these things. But it's something you've all seen, maybe without even knowing, it's in effect you'll probably know. This is something traditionally called thin film interference, but if you've ever stared at a bubble and noticed that there's shimmering colors based on the surface, that's the exact same thing. It's just the thickness of the outer kind of shell of the bubble is just roughly the same size as these layers within the beetle shell. So it interacts with the light in the same way. And again, if you've ever been out on a rainy day and seen an oily puddle, those colors, those are just the oil sitting on top of the water and being very, very thin and interacting with the light. And what you see, at least in this image here, is the color changing because this is on a slight angle. So the oil is pooling this way and becoming thicker. So to just give you a real life example, this is some images I took when we were back in the lab. This is a rose chafer. It's a nice green beetle. So this is looking up dead close at it, the surface of the top of it. You can see this green reflective surface. And unfortunately, I moved over to a Linux computer for today, and it's done something a little bit to the colors. So they're a little bit duller than I'd hoped. But I'm sure you get the idea if you've ever seen one of these rose chafer beetles before. They really are quite bright and shiny. And so when you zoom in, you get this really nice green color, along with all the surface markings, including things like scratches and whatnot. And if you move over to the leg, you start to see something kind of interesting. So on the leg, there are these regions here that are kind of pointing outwards. And as the color moves along, we see the same thing we saw in the first beetle, which is the color moves from green to a kind of a darker orange. And then if you look real closely, you can start to see hints of red as well. And this happens towards all of the edges. You can see this most prominently on the sternum, I guess. I'm not quite sure what the word for this bit is, but this is looking at the kind of the chest area. And you can see here, this is green, moving to this yellow, moving to this red. So what we're actually seeing there is, as the structure is curving round, we're looking at it from different angles and we're seeing different colors. So you can imagine this is kind of a hemisphere that we're looking at from above. I also wanted to point out that he's got quite a magnificent beard, which I wasn't expecting. They're surprisingly hairy, these beetles, when you get them under the microscope. So yeah, as I say, these are multi-layer reflectors. They really do produce just a huge range of colors. Really, everything you see in beetles is probably some sort of multi-layer reflector. Nearly everything you see. Each layer is actually around something like 500 times thinner than the human hair. So when we look at these microscope images, these are really, really stressing the absolute limit of what we can see. So these lighter areas, they're around, as I say, 500 times thinner than the human hair. And they can even create more complex colors. So things like gold, silver, and white, they're actually quite hard colors to make structurally, particularly white, because white is a combination of all colors, and it's hard to make a white that isn't just a reflective mirror. But that's another discussion. It's kind of interesting, but they can do some very complex things with these structures. And again, you can find them just by looking for metallic appearances and looking for colors that are adjacent to each other in the wavelength spectrum. I wanted to make it so that you might have a chance to actually see some of these out in the wild. These are all UK species that exhibit these colors really, really strongly. Some of them are a little bit rarer, some of them are more obvious, but just worth keeping an eye out next time you're looking at beetles. Let's see if you can find a few of these. We've got the blue mint beetle, the thick-legged flower beetle, the rosemary beetle. And I just kind of wanted to point out, it's a little bit odd that when I was looking for UK species, I had a lot of trouble finding a red beetle. You can find all sorts of exotic red beetles, but none within the UK. So that's kind of an interesting point. So moving on from beetles to something else, the multi-layer reflector property that I showed you earlier, this explains a lot of structural colors, but not all of them. Others use these more complex nanostructures. So again, it's the same thing. There's very little pigment involved. But what's happening is there's these very, very fine architectures that are interacting with the light and affecting how we see them. So butterfly wings are a really common example. This is probably one of the reasons people started looking into this field in the first place, is because they're so visually striking that very quickly it became a source of inspiration. This one, in fact, is the green hair streak butterfly. It makes these very, very complex layered structures. I believe it's technically called a hypergyroid structure. If any of you have ever used a 3D printer, for instance, you'll find that these are very good for printing packing within the structure to make it nice and strong. But this actually gives it this nice green color, this really sharp green color. And in general, when things get more complex, all they're trying to do is highlight specific colors more efficiently. And just another quick example is the peacock butterfly. So one a bit more common. So the kind of Latin name for butterflies, and do correct me if I'm wrong here, is Lepidoptera. Never been good with Latin. But effectively, this just means scaly wing. This is because early on, when we were looking at them under the microscope, we found very quickly that they had these kind of reptile-like scales on their wings. And here's a kind of a blown-up version of them on their own, away from the wing. And then even within those scales is where the structure actually is. So there's again another layer of complexity added to it. This is very common across butterflies. But in particular in the peacock butterfly, which I guess if you can imagine just the colors going on there, it is very striking. And in terms of what they found in the literature, it's that this one is actually a combination of both structural color and pigmented color. So they have these very complex structures, and this lower layer is actually colored in such a way that it enhances the reds and the blacks and the blues that are coming off them. So again, it's they just keep adding more complexity to make these colors work. Again, moths on the other side of things, just so they weren't left out, they displayed a much similar structure. So again, these tiny scales, and this is a golden purple moth that you can see actually within the UK. I've never seen one myself, and I was quite surprised because it's, you know, as I said, gold is a very complex color to make. But there's a lot of these ones that aren't really represented in the literature, despite how similar they are to the butterflies. So moths are sadly a little bit overlooked, but when you look at things like this, it's hard to wonder why, because they are very, very visually striking. Again, this is a combination of structure and pigment, so a very complex structure, but you can start to imagine there's some really amazing possibilities that just haven't been looked at yet. So the bit you all actually wanted to hear about, Nacre, it's a very fantastic material. And I kind of set this talk so that I could talk about the beetle thing because it's the simplest version of it, and then it slowly kind of ramps up in complexity. And now we're reaching the portions of it where my knowledge is limited and knowledge is limited in general, just because this is an incredibly complex structure. So it's an organic and inorganic compound produced in some mollusks. Effectively, it is a series of plates that are 10 to 20 microns wide and half a micron tall. Again, to give that some perspective, the human hair is around 100 microns in thickness. So looking at these microscope images, you can start to imagine it. It's like an overstocked bookshop where all the books are laid on top of each other, and to pull one book out is to cause chaos. But all of these bricks that are these platelets are held together by these biopolymers, these things I was telling you about before. So chitin is an example, lustrin. This all changes a lot between species. It's hard to make definite statements, but in general, to get the kind of the pearlescence that we see from a lot of shells and the mechanical strength that we see from shells, it's often this brickwork-like structure. So this is it up here. It's actually an incredibly strong structure. As I say, it's very mechanically strong. It's very resistant to outside perforation. And if you measure the strength of these structures within the mollusk world, they're actually 1,000 times more strong in this kind of layout than they are just on their own, which is kind of fascinating. So there's a lot of thought been put into this. As I say, it's very similar to this kind of brickwork structure. But again, if we follow that analogy, the weird thing here is that the kind of brick to cement ratio is actually 95% to 5%. So 95% brick and only a very small amount of cement. So maybe think about that next time you look at a brick wall. It's probably got to be more something like 70-30 for actual architecture that we make. So it's very strange that these things are so strong and they hold together so notoriously well. The weird thing in terms of color, at least for me, is that the length scales that it works on, these micron length scales, they are much bigger than the beetle. So before, the beetle was working on kind of nanometer scales. This is working on kind of micrometer scales, which are 1,000 times bigger. So the colors that we see, they are not actually optimized for brightness. It's almost like the pearlescence and the kind of colors that we see from them are actually a side effect, an unintended side effect. And this is something I'd love to hear your thoughts on, because well, I'll go over some examples in a minute. But it seems like a lot of the time that this effect is quite hidden by other layers on the mollusk. So we can talk about that in just a second. But if you were to take one where it's not hidden, sorry, I'm dead thirsty today. Take one where it's obviously not hidden, such as this one here, which is this shell from French Polynesia. So it's quite an exotic shell, very visually striking, very blue, very purple. And then this paper that was done in here, 1999, they decided to look into why exactly this is just so striking. The mechanism is exactly the same. It's these micron level changes, in this case, these structures laid on top of each other here, and they act as a source of diffraction. This means that we don't typically see these in other species. I've suddenly lost my voice, I'm very sorry. I'll try and keep going, but if I start to sound more hoarse, it's I'll keep drinking. Yeah, so these structures here, they are different to what I showed you before. This isn't this brickwork structure, this is the surface structure. So underneath this structure is the brickwork structure that is very, very strong. But this, where they have these ridges and these lines, this is acting in a way to color the surface in a similar manner to before. And this kind of leads you to believe that there is actually a huge amount of variation between species. There is a lot of different structures going on here. And it's very hard to make a kind of a judgment from afar without looking at these things under the microscope. To back that up even further, I thought this was quite fun in preparing for this talk. The iridescent color in Nacre includes thin film interference, grating diffraction, a combination of these two effects, and a one-dimensional photonic band structure. So here they're talking about what are the structures, what are the mechanisms by which we see this pearlescence in shells and seashells and whatnot. And really their answer is, well, there's a bunch and they're all competing against each other. And sometimes they're present and sometimes they're not. And this could really describe exactly why there is such a huge range within nature. And describe many of the different types of nacre we see, and maybe some of the geological differences. So I'd be interested to hear your thoughts on that as well. But just to give you some images that I took myself, this is the flat top shell. My family is currently on the south coast, and you can find these all over the place. But as I was saying before, the color's actually hidden. So this pigment on top is not structural color, it's just colored calcium carbonate. And if you ever find a dead flat top shell, they usually have the tops ground down a bit. So you put these under the microscope and very quickly the color emerges. You can obviously tell there's colors there, but it was hidden by a layer of pigment for some reason. Apologies for my voice, everyone. But just an example for next time you're at the seaside. And from there, I kind of wanted to just show you some of the kind of material science that is going on. So on the left here is some actual nacre. And on the right is some artificially grown nacre. Oh. So there's lots of work attempting to mimic the strength of it, but not so much the optics. So it was nice to find a group that were doing the optical side of things. As an aside, you may have heard me use the word diffraction. This does happen in nacre. It's one of the causes of the color. And to just kind of give you a real world example of that, if you take any CD or DVD, you'll have seen this rainbow pattern emerging from it. It's the exact same thing. It's a micron scale structure on the surface. I'd highly recommend following this guy, Ben Krasnow, on Twitter, or go to see his YouTube page because he does some amazing things, such as looking at vinyl record players under the microscope and how the needle interacts with the groove. Get stuck. Okay. So hopefully you can see a video. Let me know if this is not the case. Oh, okay, not working. We've got to start. So I'll start talking and hopefully it'll catch up. These diffraction coatings, like I showed you, the ones on the CD. On eBay, you can buy a sheet for £3 that effectively does the same thing. So it's a rainbow. I might have it here actually. 1 second. I don't know if you can see this. Ooh. Yeah, this is a diffraction grating sheet. They've used a laser to etch 35,000 lines per inch into the surface. And effectively, this does the exact same thing as the Nacre does. 1 second, technical difficulties. I seem to be stuck. Oh, it's going so well, other than me losing my voice. Just bear with me a second. It's not responding. Okay. Can everyone see that? Exact same thing as seashells. All I've done is I've used my 3D printer to just print onto this. And the molten plastic takes the structure on. You just peel it off and it has this really nice rainbow finish. And you can do that with all sorts of materials. So the other material I showed you there was a gel, a biological material that you can embed this color into, and you can make seashell-like gels. But other than that, let me just take a quick flick through the slides to see if there's anything else important. If you want a really easy to find version of structural color, pick a buttercup. Buttercups have structural color in the bottom of the petals. That's why you get that reflection on the bottom of your chin when you hold it up to it. It's literally light reflection happening. But yeah, apologies for the kind of sudden end, but I think that's everything I wanted to cover. Thanks so much for listening, everyone. That was a journey, wasn't it?